So in the previous lecture, basically we discussed comparison of convergence in two nonlinear spaces or convergence in matrix spaces. So either we compare the nonlinear space or we compare matrix space. That is same thing because norms are related to matrix. We know what is the relation. So we are going to consider the vector spaces on which we have norms. So we say that the first norm is stronger than the second norm if every sequence xn in x, xn converges to x in the first norm implies xn converges to x in the second norm. So that means whenever xn minus x converges to 0 in the first norm implies xn that sequence whenever it converges in first norm it must converge in the second norm. So that is the first norm is stronger than the second norm. And then we characterize this criteria that when a norm is stronger than the other norm. So for that we need to find a fixed number, positive number alpha, such that first norm is less than equals to alpha times second norm for every element x in the vector space. So we discuss some examples over Rn. So Rn or Cn, we have three norms defined: one norm, second norm, and infinity norm. One norm, two norm, infinity norm. So one norm is basically taking modulus value of each coordinate and adding them. Second norm is taking modulus square of each coordinate, adding them and taking square root. That is the Euclidean norm. And then the sup norm, or since there are only finitely many coordinates, supremum is maximum. So maximum of modulus of each coordinate. So we have checked that the first norm is stronger than the one norm is stronger than two norm. Two norm is stronger than one norm, and alpha turns out to be root n in that case because here what is n? N is the number of coordinates. Yeah, so if you take R2, then n is 2. So that means norm x1 is less than equals to root 2 times norm x2. Yeah, similarly, we compare other norms, and I have given this exercise. So which is very simple. Just write for R2, and then you can extend it for Rn. So topologically, all these norms are same, but geometrically they are different because the unit ball is different for these three norms. So that we already noted, and that was that quiz exercise. Okay, so then we discuss continuity in the non-linear species. So continuity in non-linear species, we know that in non-linear species, any linear, if we have a function f from x to y, not necessarily linear, if we want to show it is continuous, we need to check this condition. Whenever, so this is a sequential form of continuity because whenever we have a non-linear space or metric space, we can use this definition of continuity in terms of sequence. But here f is not necessarily linear function. So if we assume one more condition that f is linear function, then instead of checking for all sequences, it is enough to check for only those sequences which converge to 0. Right, so that means we need to check continuity at x0 is equals to 0 only. Because if xn converges to x, we will get a sequence which converges to 0. And if this sequence converges to 0, and f is continuous, then fxn converges to fx. Right, and converge is always true. If the function is continuous at every x, then it is always continuous at x equals to 0. Right, so if we have a function f from nonlinear space to nonlinear space, and it is continuous if and only if it is continuous at origin, at the zero element, of the vector space. So that is this result, and then we discuss one proposition that says that if X is a finite dimensional vector space and if f from x to y is a linear map, so that is important. Not every map is continuous. Only linear map from a finite dimensional space, finite dimensional vector space, nonlinear space, that is continuous. That's x and y are nonlinear spaces. X is finite, domain is finite, and f is linear, so it is continuous. So, so example, we know if we take x equals to r and y is equals to r, and we define a function so up to origin this it is this function, and then origin onwards it is this function, right? So at 0 the value is -1, right? So if we take this function, then f is a function from r to r. Is f linear function? Is this function linear?
Sir, if f would be linear, then it would be continuous. But the last theorem, according to last theorem, so it's not linear.
Without using that theorem, from the graph itself, can't you see that it is not linear function?
Yes, sir.
Right. So from graph itself, it is clear that it is not a linear function, because if we take any function from r to r which is a linear, it must be a line. The graph must be a line. So this function is not linear, and therefore, yes, f is not linear, right? And from the graph itself, it is clear that f is not continuous at 0. So theorem also we can apply, but uh, here we are discussing through graph only. So that is just the example. And then we take another example in which we have a fx. So f from r to r, f is linear function. So let us take fx equals to 2x. Yeah, x equals to 2x. So this is a equation of line. So at x equals to 1, value is 2. Right. So this is y is equals to 2x line. And from the graph itself or the definition of function itself, f is linear. So is f continuous at 0?
Yes, sir.
Right? And in fact, f is from the graph itself, it is clear that f is continuous everywhere. So what is important between between this graph and this graph is that we are taking the linear function. Right? So linearity implies continuity, that is this result here. So yeah, but here it matters what is the domain. right? So domain we are taking one dimensional. So it is a finite dimensional, therefore it is linear function. Yes, every time we cannot draw graph because we can draw graph only in R2 or in XY plane or 3 dimension. Yeah, but in general, the domain is finite dimensional. From this, we can apply this result, and there we get the function is linear implies continuity. So linearity is very important to conclude continuity in the finite dimensional case when the domain is finite dimensional. Now the second case is that when we have a infinite dimensional vector space. So question is that in infinite dimensional this is not true. That means linearity does not imply continuity. So we were discussing one example in last lecture. So dimension of x we are considering infinite. So whenever we have an infinite dimensional vector space, we can always find a linearly independent subset of the infinite dimensional vector space. So here in L2, we know that this is a linearly independent subset which consists of infinitely many elements. So first of all, what we will do is we from the infinitely many linearly independent elements of the vector space, we will that set is L because it is Li set, so we call it L. And that Zorn's lemma we have discussed one proposition that says that if we have a Li set, we can always extend it to the basis of the vector space using Zorn's lemma. Right. So this is application of Zorn's lemma that using Zorn's lemma we can extend the Li set to a basis. Right. So B is a basis, and from all the elements of basis, so L is a subset of B, right? Because we are extending linearly independent set to a basis of the vector space X. So if we have an element of L, on those elements we are defining value of the function to be y naught, where y naught is a non-zero value of the codomain. And if we have elements of B which are not in L, right, that is this condition, then on those elements we are defining value of the function to be 0. Right, so it is kind of identifying whether the point belongs to L or which is not in L but it is in B. So kind of indicator function. So extend f to x by linearity. So now once we know the definition of function on the basis, we know from the linear algebra that from the basis element we can extend this function on the whole space by taking all linear combinations. Right, so from linearity we can extend f to x, and so we get a linear function on x which satisfies this condition for the basis element. So now we have constructed this sequence. So this sequence is elements of x because they are linear combination of xn, right? They are some number times xn, and xn are basis elements. So this is linear combination of basis elements. They are elements of x, and on those elements, if we apply the function, yeah. So this sequence converges to 0, but when we apply the function, so this part I have, yeah. So there was a confusion. So let us change it. So what is fxn? F whenever we apply on the non-zero elements, it gives the value y naught. Right. So why it is y naught? Because Yeah, so that is the condition coming from the LI set. Okay. So yeah, so what I have written is fine. So that is 1 upon n times norm xn fxn. Now this fxn is y naught. So this is y naught divided by n times norm xn. Y naught is a constant number. So this does not converge to 0. So yeah, so this doesn't converge to 0. Is it clear why this doesn't converge to 0?
So if you can explain one more time.
Yes, that is what I'm saying. So there is some doubt. So let us take one example of this. That will be better. So so at this point, I also have doubt. So let us construct some function which satisfies this property. So we have discussed x equals to c naught naught, and uh, yeah. So if we take, we know that c naught naught is infinite dimensional vector space, right? Why it is infinite dimensional? Because it has a infinite Li sets. So let L is equals to E1, E2, En. So this is an infinite Li subset of C00 where En is 0, 0, 0, 1, 0, and so on. So this is nth element of the sequence. Alright, so this nth element is 1, other elements are 0. Now if we define this function, so define, yeah, so since L is an Li subset of C00, we can extend L to a basis B of C00, right? But in fact, L itself is a, in this case, L itself is a basis. Yeah. So L is Li said, is it clear?
Yes, sir.
Hmm. Now, what will be the linear combination of like elements of L? So linear combination of elements. So basically, here we are taking finite linear combination, right? Whenever we discuss basis, uh, definition of basis, we take finite linear combination of elements of L is of the form. So what is the combination? Combination is summation alpha I ei, right? But this I are not the E1, E2, En. It may be any of the E1, E2, En. So that means we'll write I alpha ik eik, where k is running from 1 to n, right? So that is nothing but alpha I1 ei1 plus alpha I2 EI2 alpha IN EIN. So this I1, I2, IN are any natural numbers, and for that we get the sequence 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on. So the first number is I1 entry, second is I2 entry, third is I3 entry, and so on. And at I1 entry, the coordinate is alpha I1, right? At the I2 entry, the coordinate is alpha I2. Here the coordinate is alpha I3, and so on. So there are n such non-zero elements in this sequence. So what is this sequence? This sequence is basically the sequence which are all elements are zero except finitely many entries, right? So we get all elements of C00 as a linear combination of L. So therefore L is a basis for C00. Right. So L is a basis for C00, and then once we have a basis for C00, we can define a function. So now define f from C00 to, let us say we are taking one-dimensional vector space, right? So now in this vector space we have a non-zero vector. Why not? So that we are taking one, the number one. So define this function on the basis elements by, so how we define E of En divided by n, right? That is this element xn divided by n norm xn, but En has norm 1, so that means this is nothing but En divided by n. So f of En divided by n, we are defining it to be non-zero value, any non-zero value for every n. Yeah, so first we define it on the basis element, and then we'll find this. Yeah, so this happens, right? So this definition on the every basis element, and using that, what is f of En divided by n? That will be n times f. Yeah, so that is correct. Instead of defining on f En, we are defining f En by n. So if we define f En by n to be 1, then we will get f En to be n. Right? That is correct. So there is some trick here. So if we define Fen by n, what will be this? Fen is 1, so Fn by En is 1. So therefore, we are getting 1 by n. We should not get 1 by n. So therefore we need to define this function. Yeah. So yeah, so this way we can define the linear function. So then what is En by n? This norm is 1 by n, which converts to 0. But when we apply the function fen by n, that is a constant function. And constant function will not converge to 0 as n approaches to infinity. So why we are defining en by en here, en by n here, because it is enough to define the linear function on the basis element. So for example, if we have a function from R2 to R, so what we need to define is we need to define it at f of 1, 0 and f of 0, 1 only, right? And to define it at 1, 0 and 0, 1, because this is a basis, right? R2 has a basis 1, 0 and 0, 1. It is a linear span of these basis elements. It is enough to define on basis element, and to define it on basis element, it is enough to define it on the any alpha non-zero alpha times 1, 0. If you know this is k, then you can find what is f of 1, 0, because f is linear function. So f of 1, 0 is k by alpha, right? So here what alpha we are taking is 1 by n. So we are defining 1 by n times en, we are defining the function, and ens are basis elements, right? So if you know any scalar times function, we can define it on f of 1, 0, and once we know f of 1, 0 and f of 0, 1, we know that f of k1, k2, that is any element of R2, that we can write as f of k1 f of 1, 0 plus k2 f of 0, 1. So to define the linear function, it is defined to define the function on the basis element. Once we know on the basis element, we can define on the whole domain. And to define it on the basis element, it is enough to define the function on the scalar times basis element. And that is what we are doing here. We are defining it on the 1 upon n times en. So we have defined the linear function. For example, what is the value of f of 2, 3? The sequence. Yeah, so can you tell me what is the value? To define the function in this way, what will be the value of f of 2, 3? So basically it is f of 2 times e1 plus 3 times e2. And then we know that f of en is n, right? Using this, f of en is n. So 2 times f of e1 plus 3 times f of e2, and that is nothing but 2 times 1 plus 3 times 2. So the value is 2 plus 6, that is 8. Yeah, so now is it clear? Any doubt regarding this?
Sir, FE1 value and FE2 value, how you have taken?
So we are taking Fen by n is 1. The same way what we have discussed here. Fen by n is 1. And f is a linear function. So that means 1 upon n we can take outside. So that is basically f of En we are defining by n. So either you define f of En is n in this definition, or you define f of En by n is 1, that is same thing.
Okay, sir. Thank you, sir.
Right. So that is what we are defining. The function we are defining on basis element. And now it is more clear that whenever we define f of En is n, En by norm n is 1 upon n, which converges to 0. But f of En by n, that is, let me write one more step here, that is 1 upon n times Fen, and that is 1. Which does not converge to 0. So we have a sequence which converges to 0, but when we apply function on that sequence, we are getting constant term, constant non-zero term. So this is a constant sequence 1111 in the codomain, and it in fact converges to 1, so it cannot converge to 0. So therefore f is not continuous. So f is a linear function, but f is not continuous. So why? Because the domain is infinite dimensional, right? So domain is infinite dimensional. So yeah, so now this thing we can, yeah, so here what we are doing, we are defining again here on xn divided by n norm xn to be 1, right? Why not? And then when we apply the function, its value is, what we are getting is 1. 1 means why not actually. So that is non-zero. Yeah. So same argument works here. Anyway, so our objective is to just discuss one example that this result does not hold in basically infinite dimensional. That every function need not be continuous when we take the domain to be infinite dimensional. Yeah, so what is the equation of this function? We define f of En is n, right? So if we take the linear combination, we observe that any linear combination of this function is of this form, right? Any linear combination of the basis element is of this form. That means we have this type of sequences. So what will be the expression of the function on this? So in the example of C naught naught, f we define on elements of C naught naught, right? So for x belongs to C naught naught, f of x is basically f defined on the elements 0 0 0 0 alpha I1 0 0 0 alpha I2 and so on, right? So only finitely many non-zero terms. So let us write down that 0 alpha I3 0 0 dash up to ik. Right, only alpha 1, alpha I1, alpha I2, alpha I k are non-zero numbers. When we apply, yeah, so what is this? Basically, it is summation alpha ik eik. This is n alpha ik eik. When we apply f, we know that this is alpha ik f of eik k1 to n, right? Because f is linear, so we can take scalars outside, and then what is eik? So en, we define f of en is n, right? F of en is n, so that means f of eik is ik, right? Because f of n is n. So now what is this function? This function is basically k1 to n ik alpha ik. Right. So basically what is happening, we consider this coordinate set x1, x2, xn. Then this is the alpha ik coordinate, this is ik coordinate, and in general, if we apply f x1 x2 in C00, f of x is basically the coordinate times ik times xik. Right. So alpha ik is what? Alpha ik is basically the ikth coordinate. So this is the expression of the function. Which is not continuous. So we will be using this function later on. What this function is doing, this function is keep increasing. So basically f of en is n, right? So value of, as n increases, it is increasing. So f of e1 is 1, f of e1000 is 1000, right? So that is the reason why it is not continuous. So now the question is that every time we cannot define such a linear function. So how to check whether the linear function is continuous or not in infinite dimensional case, and the domain is infinite dimensional? Because if domain is finite dimensional and it is linear, then it is always continuous. So let x and y be non-linear spaces and let f from x to y be a linear function. We have a linear map from a non-linear space to another non-linear space. So then following statements are equivalent. So first statement is that f is bounded on some closed ball around 0. So what is the definition of bounded function? Yeah, yes. What is the definition of bounded function?
The function is bounded above and below.
Yeah, so basically we take modulus fx that is less than equals to some number, fixed number alpha, right? So that is exactly it is bounded below by minus alpha and above by alpha, where alpha is some positive number. So in for linear function also, now we are going to define the boundedness. So instead of saying fx is less than equals to alpha, we will use norm of fx is less than equals to alpha times norm x for some positive alpha. Right, so this is basically the boundedness of a linear function, and it is related to the continuity of the function. So that is what we are going to prove in this statement. So let us write down the statement first. So first condition is f is bounded on some closed ball around 0, centered at 0. Second condition is f is continuous at origin. F is continuous on x. So we have seen that these two statements are equivalent. Right. If f is a linear map, then these two statements are equivalent, whether we check the continuity at every point or we check continuity at origin. Both the conditions are equivalent. Fourth condition is whenever the function is linear and continuous, it is automatically uniformly continuous. Yeah, so what is the definition of uniform continuity? What is the difference between continuous and uniformly continuous function? So if you remember, then uniformly continuous also we define also. So uniformly continuous means basically in continuity delta depends on the points where we are checking the continuity as well as epsilon. But in uniform continuity, delta does not depend on the point which we are taking. It only depends on epsilon. So one standard example of uniform continuous function is Lifshitz function. Right. So if you remember Lifshitz condition, that condition is very similar to this condition for the linear maps. So that is this last condition. So we want to prove that all these 5 conditions are equivalent, and some of the cases are very trivial. So for example, uh, yeah, so let us start with some of the parts. So one part is very clear that if it is continuous at 0, it is continuous at 0, then it is bounded function. Right? If you remember that every continuous function is bounded. So that we are using in the 2 implies 1. So, and whenever such a alpha exists, it is uniformly continuous. So that part is also very simple. So for example, so 5 implies IV. If 5 is given, then we get this alpha greater than 0 such that this holds. What is norm of fx minus fy? So remember, f is linear function, so there is f of x minus y, right? And then x minus y, if we substitute here, we get alpha, it is less than equals to alpha times norm of x minus y. Right, so this is true for all x and y. And whenever this inequality holds, we get f is Lipschitz function. So basically this condition is related to Lipschitz function, but what we want is, we want for every epsilon greater than 0, take delta to be epsilon by alpha. So in that case, we have, whenever norm x minus y less than delta implies x minus y less than epsilon by alpha, and therefore fx minus fy, that is less than equals to alpha times norm x minus y, and that is alpha times epsilon by alpha, that is alpha, that is epsilon. Right, so what we get is, essentially we get uniform continuity, because delta does not depend on which point we are taking, it only depends on epsilon and alpha, right? So therefore f is uniformly continuous. So this part is simple, just we are using this alpha condition. So this condition is known as f is bounded. F is bounded as a linear map between nonlinear spaces, and this boundedness condition is equivalent to the condition that f is continuous. Right, so this theorem characterizes all the continuous function on non-linear space which are linear with the boundedness condition. So this says that whenever we have a linear function on non-linear space X, instead of checking continuity, we can check only the boundedness. That means this condition number 5. So if we can verify condition number 5, we can, using this theorem, if there exists alpha, so that norm fx is less than equals to alpha times norm x, then f is automatically continuous function from x to y. Okay, so far we discussed 5 implies 4, that if such alpha exists, then f is uniformly continuous, and then we know that if f is uniformly continuous, it is always continuous. If it is continuous at x, it is always continuous at 0. And then 2 implies 1 is also true, because if it is bounded, so let us yeah, so if it is continuous, then it maps bounded set to bounded set. So have you come across such a result in matrix spaces? Okay, so let us prove this 2 implies 1. Yeah, so what other parts are simple? 4 implies 3, 3 implies 2 are simple. now we want to imply 2 implies 1, first part. So what is given? We are given that f is continuous at 0. What we want to show is we want to show that the first condition is f is bounded on some closed ball around 0. So to show that we will use the definition of continuity at 0. So therefore for every epsilon greater than 0 there exists delta greater than 0 such that whenever norm of x minus 0 less than delta implies fx minus f0 less than epsilon. Right, so now this condition, last condition is what? F is a linear function. So what can we say about f of 0? F is a linear function. So what can we say about f of 0? Yeah, am I audible?
Yes, sir, you are audible.
Okay, so if we have a linear function, what can we say about the value of the linear function at 0? So you must have seen one result in linear algebra that every linear function f of 0 is 0, right? Linear transformation. Every linear transformation maps origin to origin or 0 element to 0 element. Yeah, so that is what we want to say is that this last condition is nothing but since f of 0 is 0, f is a linear function, f of 0 is 0. So the last condition is norm of fx is less than epsilon. Right, so what it says is that whenever we have for every epsilon there exists delta, some positive number, so that whenever norm x is less than delta, so norm x is less than delta, that means what? That means we have a ball, right? Norm x less than delta is a ball. So that is closed ball, center at 0, radius delta. So that is this condition. So x belongs to this. That means norm of x minus 0 is less than delta. Yeah, it is open ball, sorry. So we are not taking closure. It is less than delta. And whenever this happens, what happens? Fx is bounded by epsilon. So the same thing, if we write in the other way, we get norm of fx is less than epsilon when x is in the ball around origin. Yeah, so this is now once this holds, if we take any closed ball inside this, then also this is true, right? So for example, if we take x belongs to u0 by delta by 2 closure, then this is certainly subset of u0 delta. Right, so if we have any ball of radius delta around origin, and if we take any ball of radius delta by 2 closed ball, so that means boundary also we are taking. So this is u closure 0 delta by 2, and this is u0 delta. So we can half the radius or take the smaller radius, then the closed ball will contain in that open ball, and since this holds for all elements of the bigger ball, it also holds on the closed ball. So that is this condition, the first condition. It is bounded on the closed ball, some closed ball around origin. Here delta epsilon is not important. The only thing we have verified is some positive number holds, so that f is bounded on closed ball around origin. So this condition is also a bit trivial. We are just using the definition of continuity at 0. So we proved 2 implies 1. Now only thing is left is 1 implies fifth part. So 1 implies fifth part means we have a this condition is given, whatever we proved. Yeah. So this condition is given that on some radius u closure 0 r, when we take x belongs to that set, norm of fx is less than some fixed number. So that is, the function is bounded on the closed ball, and then it implies that the last condition of boundedness of a linear map is satisfied. So let us prove that. Yeah, so we show that 1 implies 5. So first condition, so what is given? Given is that, yeah, so can anyone tell what is given? We are given f is bounded on closed ball around 0. So that means which condition will take? F is bounded means there exists some beta, some positive number, such that yeah, so 2 numbers we need, because we need closed ball also. So beta greater than 0 and r greater than 0, such that x we are taking in the closed ball. So let us take r is the radius of that ball. So since whenever x is in the closed ball of radius r around origin, fx is bounded. So fx is bounded by beta. Right? It doesn't matter, we take less than or less than equals to. Right? So that is exactly this condition we have taken. So here r is delta by 2 and beta is epsilon. So that delta and epsilon coming from the continuity definition. So this is given. We want to prove that f is, as a linear map, it is bounded. So f is linear map, it is bounded. That means there exists some positive number such that norm of fx is less than or equals to alpha times norm x. Right. So this is given. We want to prove this condition. So obviously R and beta is given and we need to find alpha. So our alpha will depend on R and beta. Right. So it will depend on that. So what we'll do, we'll start with any element of x. Any element of x. If we take x equals to 0, then this is always true for every alpha because f of 0 is 0. So 0 is less than or equals to norm of 0 is 0. So x equals to 0, this will always satisfied for every alpha. Therefore, we need to check basically this condition for the non-zero elements. Right. So let x belongs to x such that norm of x is non-zero. X is a non-zero element of x. So then, yeah. So now to use this first condition, x is a non-zero element. To use the first condition, we need an element whose norm is less than or equals to r. Right? X belongs to the ball centered at origin and its radius is r. So that means we need a element. Now this x is different from this x, right? So don't confuse with that. So if there is any confusion, we can take this y. So using y, we need to find x whose norm is less than or equals to r. So what element we will take? So we know the ortho, we know how to make the norm 1. Right? If we have a vector x, we normalize it. So that means we divide by its norm, then we can get a vector of norm 1. And then we have a vector of norm 1, can dilate it and we can make its norm r. Right. So what we'll do, we'll consider the elements x divided by norm x, its norm is 1, and we multiply by r. So then this element has, what is the norm of this element? Rx by norm x has norm r. Right. So that means it is always contained in this disk u closer 0 r. So what is u closer 0 r? Let us recall, that is the set of all x such that its norm is less than or equals to r. Yeah, so we have taken y, right? Yeah, so this is a mistake. It is y divided by norm y. So this is element of u closer 0 r because norm y is non-zero. And once we have this element, then we can use this equation. So whenever we have element of u closer 0 r, when we apply f on that element, its norm will be less than beta. Then this, and hence we get, and we apply f on this element, norm of that element is less than beta. So now we are done because now f is a linear function. So this we can write as r divided by norm y. This is a scalar that comes outside the linear function, that is less than beta, that is less than beta. And then again, this is a positive number which will come outside norm. So this is a property of norm. So r divided by norm y is norm of f of y less than beta. So finally what we get is norm of fy is less than beta divided by r norm y for every non-zero y belongs to x. Right, so what we were looking for, some positive alpha so that this condition is satisfied, and we got this condition for this particular alpha, right? So therefore norm of fy is less than alpha times norm y for all non-zero y belongs to x. And in fact, if we take y equals to 0 and we allow less than or equals to, this we can write for every y in x, because f of 0 is 0, right? So this holds where what is alpha? Alpha is beta divided by r. So we have proved that f as a linear function, it is bounded. So such functions are known as bounded linear functions. So let us, yeah, so this result we proved, because the last part we proved 1 implies 5. So each of these conditions are equivalent. So let us just define. So let x and y be nonlinear species a function let f from x to y be a function, be a linear function. F is called bounded linear function if this condition is satisfied. So what is the condition? Condition is there exists alpha greater than 0 such that norm of fx is less than or equals to alpha times norm x for every x belongs to x. So the set of all bounded linear maps we will denote by BL XY. So what is BL XY? That is the set of all bounded linear maps from x to y. So note that this alpha will be different for different maps. Right. So for all maps from x to y, there cannot be single alpha satisfying this condition. So for different function, we will get different alpha. And what the previous theorem says that every bounded linear function is always continuous. right? So what is CLXY? CLXY is the set of all. We are saying continuous, but we are actually assuming linear functions, right? We are only considering linear functions. The set of all continuous linear functions. So linearity is important. X to y. Okay, so this is regarding the characterization of continuity in terms of boundedness. So whenever we will require to check the continuity of a linear function from nonlinear space to another nonlinear space, now onwards we'll use only this boundedness condition. Right. So if we have a function, it is a linear function from nonlinear space to another nonlinear space, instead of verifying in terms of sequences, checking the continuity in terms of sequences, we will just look for finding the positive number alpha such that norm of fx is less than equals to alpha times norm x. Right. So all of these conditions, the continuity definition, there is one more characterization other than this fifth characterization, and other than this four characterization of the continuity. The last characterization is in terms of the quotient spaces. So you remember the definition of quotient space and quotient norm, which we defined earlier. So that is characterization of continuous linear map in terms of quotient spaces. Quotient space or quotient norm, basically. Quotient map. So far we discuss only quotient space. Now what is quotient map? So let us start with, let x and y be non-linear spaces, and f from x to y be a linear function. Yeah, so f from x to y is a linear function. So now what is we know that zero space of f is a subspace, right? Zero space of f is a subspace of x. So what is ZF? ZF is the set of all x in X such that fx is 0 is a subspace of X. Right. So if when ZF is closed, right, every time it may not be closed subspace. So whenever ZF is closed, we can define a new map related to f. So f is the given linear function. So using given linear function, we can define a new map f tilde from the quotient space to y, right? And we can define this function by, so we know that f tilde is applied on the element of the quotient space. So quotient space, we have elements x plus m. So m is zf, right? X plus y, where y is a subspace. So the subspace is this kernel basically. So on the elements of the quotient space, which looks like this, we are defining the function f tilde to be fx. So what we are going to prove in the next lecture is that, let me write the statement only. So we want to prove so let f from x to y be a linear map where x and y are nonlinear species. Then f is continuous if and only if the kernel is closed. And since the kernel is closed, we can define the function f tilde from x quotient zf to y defined above is continuous. So continuity of the function capital F is equivalent to the continuity of f tilde, which is, so f tilde is basically the quotient map corresponding to given linear function. So every linear function has a kernel zf, and with respect to zf we take the quotient space, and on that quotient space we can define f tilde. Okay, so this result we will prove in the next lecture on Monday. So if you have any doubt, you may ask now.